Swayam Prabha. Digital India. Educated India.
Okay, welcome back, and let's continue the discussion on the laminar non-premixed flame. So, we are looking at the jet diffusion flame and doing the detailed analysis and trying to find out the profiles and all these things. So, this is where we stopped on the boundary conditions and all these things. So, this is the jet, unconfined jet where fuel is coming in, and then with some of the assumption we got to the conservation laws and mass, axial momentum, species, and then we have one from the oxidizer, and then we note down the boundary condition. One of the boundary condition is the along jet center line, and then at the large radius jet center line we have radial velocity is 0 and the derivatives are 0, which is from symmetry. At large radius axial velocity is 0, fuel mass fraction is also 0, and then at the finally we have this jet exit, where we assume the uniform axial velocity and fuel mass fraction and 0 elsewhere else. So, that will get you this boundary condition. Now, the for solution the velocity field can be obtained by assuming the profiles to be similar. Secondly, the intrinsic shape of velocity profile, the intrinsic shape of velocity profile is same everywhere in the flow field. Thirdly, the radial distribution of Vx. So, Vx Rx, the radial distribution of that, which is when normalized with the local center line velocity like this, is an universal function that depends on the only depends on similarity variable, that is r by x. So, this is a standard jet flow. So, the analytical solution exists for this. Solution for the axial velocity is Vx is 3 by 8 pi mu x 1 plus xi square by 4. So, this is for the axial velocity. Now, similarly for radial velocity, solution is 3 j a 16 pi rho e 1 by x xi minus xi cube by 4 1 plus xi square by 4 to the power whole square. So, Je we have already defined, it is the initial jet momentum, which is rho e v square pi r square, and xi is defined as 3 rho e by 16 pi j e to the power half 1 by mu r by x. So, these are the definition for initial momentum and the xi. Now, we can non-dimensionalize the axial velocity, that means in terms of V x by V e, which is an exit velocity of the jet. So, if you do that, this dimensionless form will look like rho e v e r mu 1 plus chi square by 4 minus 2. Now, the dimensionless center line velocity, it decays. Okay. Now, this can be obtained by setting r equals to 0. If we put this where xi equals to 0, V x 0 by V e is nothing but rho e V e x by r minus 1. So, this is what we get. Now, what it clearly says or shows that this relationship, how the central line or velocity decays. The velocity decay actually inversely proportional to the axial distance and jet Reynolds number. So, the jet Reynolds number is defined as rho e v e r by mu. So, if you put it, so this is proportional to the jet Reynolds number and inversely with the axial distance. Now, from this expression one can also see that this is the 7 point, the solution of 7.3, it is not valid near the nozzle. Why? Because at a small values of x, the dimensionless centerline velocity, that is this is for small values of x, this quantity becomes greater than 1, and this is a condition which is actually not possible, or rather one can say it is a physically impossible scenario. So, this cannot happen. So, that is one can see this dimensionless central line velocity along this axis, which will plot dimensionless central line velocity and the axial distance. So, you can see for this size is the increasing jet Reynolds number, and with the increasing jet Reynolds number you can see the pattern, because it should not increase or goes beyond 1, which is not physical and also feasible too. Now, so the other parameters which are used to characterize the jets are the, one is spreading rate and spreading angle, which is alpha. So, these are two more important parameters which are often used to define the or characterize the jet spreading rate. Also we can introduce jet half width, which is R half. Now what is half width? Half width is the, one can see that half width is the radial location where jet velocity has decayed to 1/2 of its central line value. That means along the radial directions it is basically width. So, you find the radial width where the jet velocity decays to 1/2 of the central line value. This is what one can term as an half width. Now, this R half or half width can be derived by setting this Vx by Vx0, and so then one can say jet spreading rate is nothing but R half by x. So, one needs to find out the half width, and jet spreading angle is the angle whose tangent is the spreading rate. So, jet spreading rate would be R half by x, and jet spreading angle would be angle whose tangent is the spreading rate. So, you can see this is our spreading angle, and this is the half width, and then along this R half by x will give you the jet spreading rate. So, one can look at that thing, and this is my Vx by Vx0, how it varies with the R, that means along this direction, radial direction. So, these two quantities, I mean rather I would say three quantities, one is the spreading rate, spreading angle and half width, they are very important when you characterize the jet or rather jet flows. So, the spreading rate one can estimate it would be 2.97 rho e per, which is 2.97 jet to the power 1, and the spreading angle which will be tan inverse of R half by x. So, that is how you get one is rate, one is rate spreading rate, one is spreading angle. So, at high REJ, that means jet Reynolds number, are narrow, while low RE jets are wide, which one can see because this is inversely proportional. So, if you have high RE jet and low RE jet, you can see the difference between the spreading rate. For a low Reynolds number case, the spreading would be more, for high Reynolds number case, the spreading would be low. That primarily because it is inversely proportional. Now, we also know that when you look at the two equations 7.4 and 7.5, YF plays an same mathematical role as Vx by Vxe. if SC is 1, that is the Smith number, which means nu by d is 1. Now, if that is the situation, we can find out the functional form of the solution for YF. So, the functional form of YF is identical as Vx by Ve. So, we can write YF equals to 3 by 8 pi Qf by dx 1 plus chi square by 4 where fuel flow rate is Ve pi r square. So, this is your volumetric fuel flow rate. Now, we apply the condition Smith number equals to 1 to this equation. So, that gives back 0.375 Rej minus 1 chi square by 4 . So, that is the functional form. Similarly, one can find out the central line values of the mass fraction. So, the central line values of mass fraction would be YF naught would be 0.375 Rej. It is similar to the velocity profile. Now, again one has to note all these solutions are valid, these are valid far from the nozzle. The dimensionless distance downstream where the solution is valid must exceed the jet Reynolds number. So, which means x by r should be greater than this. Now, once we do this, we can look at the now the jet flame behavior. So, now the burning laminar fuel jet, it is quite similar to the discussion that we have done for the non-reacting jet. And to get into this burning jet, we have first looked at how the jet flames, jet flows looks like, how central line velocity profile changes and all these characteristics. Now, since the fuel is flowing along the axis, it will obviously diffuses radially outward, and the other hand oxidizer diffuses inward. So, that means if fuel goes like this, oxidizer comes like this. So, in the contact point you get the flame. So, this is exactly what the flame surface, it is the locus of points where phi equals to unity, that means along the stoichiometric condition. So, when one goes towards outside, one come towards inside. Now, this is the burning jet, this is the jet diameter and jet exit or the nozzle exit, and this dotted line. So, fuel is coming from this side. So, fuel goes like this, oxidizer come from that side. When they meet at a point, that is the locus of the flame surface, and this is the flame surface where it is stoichiometric. Outside of that, this is lean condition because fuel is going from that side. So, it is lean. phi less than 1, within that it is a reach condition, these two lines corresponding to phi greater than 1, and this height is called the flame height. So, this is the flame height. Now, if we look at the temperature profiles at this particular location, and this is at the jet exit location. So, jet exit location, you have a velocity which is uniform, temperature is uniform, fuel mass fraction is also 1, and this is outside the jet, it is all oxidizer. So, that is 1. At the this position there is nothing. At a certain downstream location, this is temperature is varying. So, this position corresponding to the location of the radial location of, if we look at here, this goes the R direction, and this is the location which corresponding to TA, flame surface. So, this corresponding to that, and this is how my fuel comes down, oxidizer comes down, and product forms. Go further downstream, this is my temperature will vary, because now this is exactly at the tip of the flame height. So, this will be the variation of the product, and this is the variation of the oxidizer. So, once you have an idea about the evolution of this jet, you can also identify these characteristics and the profiles, how would that look like, and this would also help you to understand lot of laboratory scale burner or the unconfined burners which we use later on for the analysis, and see how that evolves and all these things. Now, some points which can be noted here. One is that the products which are formed at the flame surface, that diffuse radially both inward and outward. Obviously, that would happen because products can go either side from this flame surface. What is produced, this can go this side, this can go that side. Now, the over ventilated flame is where there is more than enough oxidizer in the immediate surroundings to continuously burn the fuel, and obviously the opposite to that would be the under ventilated flame. Now, the flame length for an over ventilated flame can be determined at a location where phi are 0 and x is LF and the phi is stoichiometric. Now, also the zone of chemical reaction is quite narrow, but one can see that the laminar flame thickness, but significantly larger than. So, this is corresponding to your premixed flame thickness, which is delta. Typically, the premixed flame thickness are quite small, and that creates some challenges for the modeler. But in the diffusion case, you get a bigger reaction zone. Now, flame temperature distribution also exhibit an annular shape until the tip is reached, and the upper side of that, the buoyant forces are quite important. So, what it does, the jet accelerates, narrowing the flame, and narrowing the flow increases the fuel concentration gradient. So, that in turn enhances the diffusion, radial diffusion. So, these are some images of flame. This is a nice laminar flame. Obviously, this is not laminar, this is turbulent. This is turbulent, but this is laminar, and one can see clearly the difference between these two flame, and what is quite chaotic in nature here. So, you get different reaction zone, and in this case you get a nice shape. Now, we can ignore the effects of heat release by due to reaction. Then from 7.16 one can get a very crude description of the flame boundary. When YF equals to YF stoichiometric. So, this is a very crude description, because what we are ignoring is the effect of the heat release, which is not possible in a realistic situation. In that case, this will boils down to by dx xi square by 4 minus 2. Now, when r equals to 0, we get the flame length, and that is LF equals to 3 by 8 pi d YF stoichiometry. So, that is what you get by assuming that you are ignoring the effect of the flame. Now, the flame length, what you see, it is proportional to the volumetric flow rate of the fuel. At the same time, it is inversely proportional to the stoichiometric fuel mass fraction. Now, since we have volumetric flow rate of the fuel is V pi r square, so various combination of V and R yield the same flame length. Since the diffusion coefficient D is inversely proportional to the pressure, the height of the flame is, so that means flame height is independent of pressure at given mass flow rate. So, that is how you get the analysis of the flame height in a jet diffusion flame. We will stop here and continue the discussion in the next lecture.